Okay, so hello everyone. Welcome to the Efail talk at Black Hat. So my name is Jens Müller. I'm a PhD student at the Chair for Network and Data Security at the University of Bochum in Germany. And this guy here is Chris Driesen from the University of Applied Sciences in Münster, Germany.
Hello everyone.
And today we're going to give you an introduction to our research, which is a joint work on flaws in Mime and PGP encryption, commonly known as the Efail attacks. Okay, so what is Efail? Basically, Efail is one of the most important attacks of the year, right? Why is this? Well, you know, Efail is one of those attacks that come with a logo. Okay, and besides some clickbaiting headlines that we have seen in the press, actually Efail is a real issue, causing real trouble to email encryption as we know it, targeting the way the Mime standard and multi-part mails are handled, and the Mime standard and the OpenPGP ecosystem. Okay, so here's an outline of today's talk. First, I'm going to give you a short introduction to PGP and Mime. Then I'm going to show that back channels within email do actually exist, which are used for further attacks. And then I'm going to show and describe our attacker model. And because I don't know that much about crypto, actually, from here on, Chris will take over and explain the major contribution of Efail, which is the class of attacks, a crypto class of attacks that we call Malleability gadgets, and how to apply them on Mime and PGP. Okay, and finally, we will show some that simple way to exfiltrate the plain text of encrypted emails without even touching the crypto. Okay, let's start with a history lesson on secure email. So, you probably all know this guy. It's Phil Zimmermann, the inventor of the original PGP back in 1991. And some of you may also remember the spirit of those times, you know, the crypto wars, the 90s, when encryption was kind of outlawed, seen as something only criminals do, the US ban on exporting strong crypto and all that stuff. So some of you may also remember this event. It took place 1 month after the very first Black Hat briefings. So this is the 1997 hacking in process camp, where the PGP source code was exported to as a book. And what you can see here is some of the about 80 hackers retyping the source code from that book back into their computers, basically to bypass the US export restrictions on strong crypto. So back then, I think it's fair to say that PGP was kind of state-of-the-art crypto, and it played a really important political role to give privacy to the digital world, right? Okay, so what happened next? PGP got a standard called OpenPGP, which is used until today by privacy enthusiasts, by journalists, by hackers, and so on. And then around the same time, Mime showed up. Which is also yet another standard for end-to-end email encryption, but it's got a more centralized trust model. So Mime is often used in companies because, you know, companies, they have this hierarchy structure and it's easy for them to set up a certificate authority, while PGP traditionally follows a more web of trust approach. But besides those political differences, actually both standards currently in use for email end-to-end encryption have a lot in common. So both of them use more or less the same crypto, and both standards are from the 90s. So I guess it's fair to say that both standards that are used for end-to-end email encryption are pretty old standards, right? Okay, so you may ask yourself, why should I use end-to-end email encryption anyway? So first of all, there are those nation-state agencies which try to collect pretty much every email that routes through the internet. And I mean, we have proved this since Snowden, right? And depending on in which nation you live in, such nation-state actors, they may or may not be something you should definitely be concerned about, right? But there are some other issues. So, for example, there may be a breach of your email provider. So I know some of you guys are hosting your own mail server, and actually, without end-to-end email encryption, it's kind of a single point of failure, right? I mean, once that machine is hacked, pretty much every email is gone. And I heard something like this happen during the US election campaigns. And it's a bad thing to happen, right? And also for some popular webmail providers, you may ask yourself, do I like the idea that they are reading and analyzing my emails anyway? Okay, and now one can argue, yeah, let's just use transport layer encryption and we are all set. And before Snowden, only about 1/4 of the worldwide email traffic was TLS encrypted. Now it's much more, and this is good. With TLS, emails won't go plain text over the wire anymore, right? But we simply don't know. So from receiving an email and looking through the headers, we simply can't tell if that email was really TLS encrypted for each mail-related path, right? So the client has no influence on this. Okay, and last but not least, of course, your email account could get compromised. You could be targeted of phishing attacks. Somebody may be able to guess your passwords and so on. So we've got a lot of reasons actually to use email end-to-end encryption. Okay, so what known issues exist? So from research point of view, there's been much focus on usability. And actually, that's really an important point. Because while TLS somehow took off, email end-to-end encryption is still something for nerds only, right? I mean, it's hard to explain PGP to your grandmother, right? So while we definitely need to work on usability, also from a security point of view, there has not been that much research within the last decade. And we think this is definitely a research gap, because as said, both standards use really, really old crypto, such as Cbc cipher modes, which we know that in theory they are vulnerable to penning attacks, for example. All of you guys know this from the TLS world, for example. So in an interactive protocol such as TLS, when a client sends a message, an encrypted message to the server, it may be intercepted by a man in the middle, and the attacker may then send a modified version to that server. And then the server may somehow act as an oracle. So, for example, through timing side channels or through error messages, the server may leak, for example, the information if that modified cipher text was correctly decrypted. And this game can be played some time. So, in the end, the attacker may be able to make some guesses on the actual plain text. So we have seen this in TLS a lot of times, for example, with Drown and with Lucky 13, and lately with the robot attack, which will be presented here in the afternoon. So TLS had to constantly evolve, right? However, email encryption did not. And this is this is because it is assumed that email is just not an interactive protocol. There's no such oracle given in email, right? So we actually know that we are using kind of old crypto, but yeah, we think it has no negative impact, right? It can't be exploited. And the main reason why we think that email has never analyzed for such attacks in detail is that there was this assumption that in email there are no back channels, okay? And today we're going to show that this assumption is actually a really weak assumption, is actually wrong. Practically, back channels in email do exist. Okay, which brings us to our next topic. So we systematically analyzed email clients for back channel techniques. So for the possibility to force the email client to trigger connection to an attacker-controlled server once an email is opened. And there are a lot of possibilities to do this. I mean, all of you know those nasty HTML emails you get from spammers and marketing guys with those remote images that should be loaded so they can see if your email address is actually valid and things like that. And most email clients will not simply load those images, at least not without asking the user. But most email clients actually rely on some kind of HTML engine. And then they put some restrictions on that engine and then they think it's all fine. But HTML is constantly evolving and it's really powerful. So you could also use some other HTML tags, some other UI schemes such as FTP, or use CSS and so on. There's so many possibilities, and I think we built a pretty much comprehensive catalog to check for back channels within HTML. And then we also try to trigger JavaScript execution, which shouldn't happen in an email client, right? So we simply took the common cheat sheets from OWASP and some other sources, merged them into the email body and the subject field, just to see if we could trigger JavaScript in emaal clients. Okay, and then there's something interesting in email headers. Just like in HTTP headers, you have the possibility to add some custom header fields like message disposition notification. So, for example, the attacker sends you an email with a certain header, and your mail client may automatically respond that the email has been read. And then there are also some proprietary headers that may trigger some URLs and things like that. In the end, we had about 800 header fields 8,000 header fields collected, and actually some mail clients did trigger some URL then. Okay, we also used some specially crafted PDF files and SVGs and so on, just to see if they would preview the mail clients and if we could trigger a connection then. And last but not least, we also looked for a certificate validation process. So once an SMIME signed email is received, mail clients may perform an OCSP request or a CAL lookup to see if that certificate is still valid, right? Or they may try to download missing intermediate certificates. And well, that's actually a security feature, right? But in the context of email, the endpoints are defined within that certificate itself, and so it's sometimes possible to use those security features as a backchannel. Okay, so we systematically analyzed 47 email clients for backchannel techniques. And there are actually some email clients where we couldn't find any backchannels. So, for example, they will ask the user before loading remote content such as images. So this can also be used for further attacks, but it's not fully automated. It requires some user interaction, right? And then there were also some other email clients, the orange ones. They would simply load, for example, remote images in the default configuration. So this can be disabled by the user, but in the default config, we have a backchannel, right? And then there was this vast majority of email clients that would not load remote content and things like that, but using the approaches described in the slide before, we could bypass all of them. So for all of them, we could trigger a connection to our server once the email is read. And in addition, on 5 clients, we even had a JavaScript execution, which is something you do not want to have in email, right? Okay, the major takeaway here is that for 40 out of 47 email clients, backchannels do actually exist, right? Okay, so now let me come to the attacker model. So what is the attacker model for PGP and SMIME? It's basically the attacker model of end-to-end encryption. So assume Alice wants to send an email to Bob. So Alice encrypts that message with Bob's public key, probably also with her own public key, because she wants to be able to decrypt that email later, right? Okay, that encrypted message is now sent to Bob, who is able to decrypt it. What is our attacker allowed to do? The attacker can somehow obtain the encrypted message, so he may be man in the middle, let's say the NSA, or what may be easier is compromising the email server of either Alice or Bob, or compromising one of their mail accounts. So think of those US election campaigns, mail server hacks that happened. Okay, so now what is our attacker allowed to do? The attacker can modify that encrypted message and forward it to the intended receiver. So transparently forward it on a channel as an active man in the middle, for example, or replace that encrypted message with a modified version transparently on the IMAP server. But actually the easiest thing is to just send that modified email to Bob or to Alice, because both the sender and the receiver can act as a decryption oracle.
Okay, so as Jens stated in the beginning, we will now dive into the crypto part of the attack. So we are now looking at the Malleability gadgets. And before we can look into this new attack scheme, we have to reveal some crypto basics to understand the crypto part here. First of all, in email encryption, we use hybrid encryption. And we use this because we want to combine the advantages of symmetric encryption and asymmetric encryption. So if we have a message M that we want to send to Alice in this example here, we first have to generate a session key, and this session key is then used to do a symmetric crypto, like AES, for example, to encrypt the message. So the session key at this moment is not encrypted, so it's in clear text, and everybody could read this. So we want to encrypt this too, and therefore we are using asymmetric crypto, for example, RSA, to encrypt this session key with the public key of the receiver or the receivers and the sender. To send this now to the receiver and to get the receiver's email program know how to deal with the data we sent him, we just add a frame around this Mime frame, content type app encrypted, for example, just to get the parser to know. The receiver now gets this email and he extracts C2 ciphertext from the mail. And then to decrypt C, he needs the session key S. So he will decrypt first K with his private key. So he gets the session key S back. And then he will use this session key S to decrypt the original message. So what is important for our attack here is the part with the semantic crypto. In the semantic crypto, while we are doing email cryptography, we are using block ciphers. AES is a block cipher, and we are using here cipher block chaining. Don't worry, nothing to do with blockchains here. And we are using cyber feedback modes for PGP. And those both modes have the XOR operation as its last operation per block. So there's a decryption, and then there will be an XOR operation. An XOR is an operation that is mailable. So we have the property of those block ciphers that they are mailable. That means that if we flip a bit, or if a bit is flipped on the transport layer anywhere in the ciphertext, then a bit will flip in the plain text at the same position. Yeah? So if we flip a bit in this message we saw before, then the email here will change to Efail if we flip it right. So you don't want to have those attacks, and to prevent these, you want to have some kind of MAC, so message authentication code or modification detection code, just to make sure that nobody has tampered with your ciphertext or your ciphertext didn't get damaged during transmission. And there are several ways to implement this. There are MAC then encrypt, MAC and encrypt, encrypt then MAC, and so on. And depending on your implementation, there are again some attacks that were known to get around those message authentication codes. And we were wondering what is used in SMIME as a message authentication code or modification detection code to distinguish which attack we want to use to get around this. And we looked at the SMIME standard and we saw nothing. So there's simply no message authentication in there. It's just as it is. So now we had to look into the malleability. So we can use malleability to attack SMIME, but we have to look what we can do with malleability to actually attack SMIME. And therefore we have to go again in some crypto basics. We can look at the Cbc mode here. This is a Cbc mode example. We have C0 here, which is often called the initialization vector. And then we have C1, C2, and so on, containing the real data, the real encrypted data. If we now want to decrypt C1, we take C1 and decrypt this with the session key. And after we decrypted that with the session key, we will take C0, the initialization vector here, and XOR it to the result of the decryption to get the plaintext P0. If we move on in the chain now, if we want to decrypt C2, then we will decrypt C2 with the session key, and then XOR the previous block onto the result, so C1, and we will get P1. As I stated, XOR is a mailable operation. So if I flip a bit in the first byte of C0, then we will have a bit flip in the first byte of the plaintext P0, and we can change this here from a C to a Z, for example. Okay, what can we do with this? If we look now at the XOR table, this is the table for the XOR operation, and let's look at the first and the last column. So if we XOR a 0 and a 0, we will get a 0. If we XOR a 1 and a 1, we will also get a 0. And this means that if we know one plaintext block P0, yeah, so we know P0, then we can simply XOR this P0 block on the previous ciphertext block C0. And if we do so, we will get all zeros in P0. And that's what we call Cbc Gadget. We call this a Cbc Gadget because it's like a blank sheet of paper. Yeah, we have all zeros here, and we look again at the XOR table. If we XOR a 0 on a 0, we get a 0. And if we get XOR a 1 on a 0, we will get a 1. So whatever we XOR on zeros, we will get whatever we XORed on this. So we can do a chosen plaintext attack. So we can just choose the plaintext in P0 just by saying C0 XOR P0 to get this to null, and then XOR the chosen plaintext. If we move on in the chain, so if we do not do this in the initialization vector, but do this in the middle of the chain anywhere, like, for example, in C1, then there will be a bit flip in P1 as we expected. But the problem here is that we have changed C1, and if we now want to decrypt C1, we will get some random data. We cannot control this data, what's coming out there. So if we use malleability gadgets, we have to deal with having 16 bytes of totally uncontrollable random data, and then we have 16 bytes we can completely control. And these are the bytes we can use to build exfiltration channels as Jens described in the beginning of the presentation. So how can we use this malleability gadgets now to attack S-MIME? Therefore, we have to look at the attacker model first again. So we have Eve. Eve has obtained an encrypted email. He is now able to modify this email using those malleability gadgets or CBC gadgets. And then he wants to send this email to Bob. Bob now decrypts this mail, so simply opens this mail for reading. And the goal is now that this mail will exfiltrate itself using those back channels Jens described before. Okay, seeing this in a practical example, just put on here the beginning of an email, and S-MIME emails and in-common emails are following the Mime standard. And the Mime standard states that every Mime part has to start with content headers. So there must be defined what content type is in there. So emails will start with content type text, HTML, text plain, whatever you want. And that's the reason why we know at least one single plain text block of each email. Yeah? Therefore, we can use malleability gadgets. And if we do so, we can now just take this first block we know, and we can form a malleability gadget. And in here, we have HTML tag called base, and then there's some double quotes in the end. Now what we can also do is we can duplicate a single block. So it doesn't matter how often I took the same block and chain it after each another. It doesn't matter. So I can just chain it to build an HTTP exploit here in this case, or probably build an extension, an attachment, for example, a PDF attachment or an binary file. So I can just duplicate this. And when I'm ready with my back channel or whatever I want to inject here, then I can do a third thing here. I can do reordering. So I can take the original ciphertext and just reorder it, putting it after my crafted email part here. And because we are good coder, we love clean code, we want to close the image tag in the end. And what's happening now, maybe you can see this already. If the HTML parser will parse this HTML part, he will see a base tag and some uncontrollable things in the front. He will ignore this because it's not inside the tag. Then we have the base tag. Then we have, again, uncontrollable data, which is encapsulated in double quotes. And double quotes are ignored by the, or everything what's standing in double quotes inside the tag is ignored by the HTML parser. So what we basically have here is an image tag loading an image from efail.de/ and then it's open. Then we get the plain text we want to exfiltrate in this part here, and then we close the image tag. And so the email program will now try to load an image from our server from the address, dear sir or madam, the secret meeting will be at whatever, and this is the plain text and it's gone. So this is what we did for S-MIME, and this worked well for S-MIME and works well for S-MIME. And we were wondering if we can do this for OpenPGP too, because OpenPGP and S-MIME use a really similar crypto. And so we took a look at OpenPGP. We have some difference between S-MIME and OpenPGP here. The first main difference is that we are using not Cbc mode, but we are using CFB mode, Cyber Feedback mode. And the only difference that matters here is that we are not XORing the previous block to the actual block to decrypt, but we will XOR the next block to the previous one. Yeah? And this means for malleability gadgets, we will not get the random bytes and then the chosen plain text, but we will get our chosen plain text and then the random bytes. Yeah, not a big deal for exploiting. The next differences are a big deal for exploiting, and this is on the first hand, PGP standard has an integrity protection, so there is an integrity protection in place. And the second thing is we have compression enabled by default. This is not a security feature, but it makes the exploitation much harder. But let's first take a look at the integrity protection. PGP defines a packet format to structure their data, and we have a packet called with the tag 18 called symmetrically encrypted and integrity protected package. And this package contains a compressed data package containing the literal data then, and it contains also the package 19, and this is the package modification detection code package containing a SHA-1 hash sum to do modification detection. So we have basically here in place integrity protection since I think 2002. Before there was a symmetrically encrypted package. This is a tag 9 here. That's still valid, but most of the clients don't use this anymore. Okay, so we now were wondering how PGP standard treats occurrences if the MDC is wrong. So we looked into the standard. And the standard states an implementation must treat an MDC failure as a security problem. Okay, that's good for now, okay? But it also states the implementation may allow the user access to erroneous data, but must warn the user. And this is a problem, because if you give the user the access to the data, so show the email, and then say to the user, hey, your integrity protection is not correct, then you have already shown the mail, the HTML parser was already going over the mail and loading the image, and the data is already gone. Yeah? So this doesn't help in this specific case. So we ask ourselves, how can we go around this integrity protection based on that the implementation may give the user the data and just warn him. And there we came up with 3 possible possibilities here. First of all, we can just strip the MDC, just cut off the last 22 bytes of the package. Then we just stripped off this MDC package at the end of the symmetrically encrypted and integrity protected package. And we were hoping that the client will show the data and warn the user then maybe, but we have already the data. Also, we can just don't care about the modification detection code. So just modify the ciphertext and just don't care if the modification is incorrect. And we can also, and we tried also to do a downgrade attack, just doing an SIEP package, so symmetrically encrypted and integrity protected package, to an symmetrically encrypted package without integrity protection at all. And where we are just testing that for the email clients Jens showed in the beginning, and we've picked up here the major email clients. We will see a larger overview later. And we can see that the Outlook 2007 with GPG for Win 3.0.0 was vulnerable to the stripped and the modified MDC, but not to the downgrade. Thunderbird with Enigmail 1.9.9, as well as Apple Mail with GPD Tools 2018-01 were vulnerable to all 3 possibilities to get around this integrity protection. So we had kind of dealt with this integrity protection, and we moved on to look at this compression thing. And the compression makes our life much harder in different ways. And the first way is it's not possible for us to inject data into a compressed data packet without knowing the whole plaintext, because we don't know how the compression is done, how the symbols are defined. So we had to get around this. And we got around that. It's really kind of complicated. And if you are interested in that, just look into the technical paper or just ask us after in the rep room. We have a second difficulty here that we do not know so many plaintext bytes. So we have not this content type header in there, but we have some compressed data, and we don't know how this compressed data looks like. And we then figured out that we do not need the whole 16 bytes, what is the block size of AES, but it is enough to know 11 bytes to get some working exfiltration channels here. And it's stated that we only know 4 bytes exactly, because these are the bytes of the compression package, which say us which compression is used and what compression level is used and so on. So we have to guess at least 7 bytes to break this PGP inside email encryption. And this is kind of a huge number, but we find out that we can do multiple guesses per email. and that's pretty cool. We can just use the MIME part, so the MIME structure in email as in, to do some sub-emails here. So we define a multi-part mix here with a boundary, and between the boundaries we can place multiple ciphertext for multiple emails, so multiple guesses. And we found out that the number of guesses we have are between 500 and 1,000 submails for most of the clients that are feasible to decrypt. So we can actually do 500 guesses per single mail. Okay, then we were wondering how realistic this is. And we were looking at 2 real-life examples to get a feeling how realistic this is. And the first one is a really structured one. And this is a Facebook password reset email. Facebook enables you to upload your PGP public key to encrypt those emails to you. And these emails are looking all the same. And we looked into the template and we found out that there are 3 parts that were changing from one mail to another. It's on the one hand the border, which is fully random. Then we have of course, the password reset token is changing, and we have some kind of tracking code inside the tracking pixel. So there are 3 parts that are changing, and we then took this template, generate 100,000 password recovery emails based on this template, encrypted them with GPG in default configuration, made sure that the mail we encrypted is you cannot differentiate this mail to a mail we have generated, and then we looked at the first 11 starting bytes to get a feeling if we could do such an attack there. And it stated that there are 211 possibilities for the first 11 starting byte, which means that we can break 100% of these Facebook password recovery emails within a single mail containing 211 sub-mails like this to the user. Okay. After that, we wanted to look at a more realistic example from real-life communication, and we took the N1 dataset here. The N1 dataset is a dataset of approximately 500,000 real emails from company communication. And we took this email dataset and just encrypted this with GNU-PG again, and looked at the first 11 bytes here. And we found out that within the first 500 bytes, what we can do in one single email, we can break 41% of the whole N1 dataset email communication. Okay, as I stated before, we can now see a small overview over which clients were affected and which clients are not affected from the time of the disclosure. And we have here in the first column the S-MIME, in the second column the PGP, PGP divided into the 3 possibilities. Red is on this page the exfiltration channel without user interaction, so the user has nothing to do but opening the mail. The orange ones are exfiltration channels with user interaction required, and the green ones are exfiltration. There are no exfiltration channels. Yeah? And if we look now at the major email clients, we see there's a lot of red color in here. Okay, so as a conclusion of these crypto attacks, we want now to look at what has happened since we disclosed this to the standards of S-MIME and OpenPGP. And what we can see is that there are 2 new drafts for both S-MIME and PGP. S-MIME references to the paper, and it recommends the usage of authenticated encryption using, for example, AES GCM. So they do something against these malleability gadgets. And also OpenPGP has changed a lot. They want to deprecate this symmetrically encrypted package. They propose to get authentication encryption with associated data. And they also changed this part we saw before. Their implementation should not allow users to access this erroneous data. And during our research, so while we were struggling with this OpenPGP compression thing and struggling with S-MIME, sometime Jens came along and said to us, what are you doing there with this crypto fancy stuff? I think I have a far easier way to attack the email crypto without even touching the crypto.
Okay, so back to the simple stuff. So Efail also covers an attack that we call direct exfiltration. And that one is possible because some popular mail clients render multi-part emails within the same document and within the same HTML document. that is then presented to the user. It's kind of a natural way of implementing the Mime standard, but it's really dangerous when it comes to encryption. And so this attack is actually independent of the used encryption scheme, so let it be PGP or SMIME or whatever. And it works directly it works in Thunderbird, for example, since the very first version, so really old. And it also works in Apple Mail and the iOS Mail app and some other mail clients. And the main problem here is that the standards give no definition for how to handle or not handle partly encrypted content that is somehow wrapped within the MIME tree. Okay, so how does direct exfiltration work? So assume Alice wants to send an encrypted message to Bob, so her email client will simply encrypt the plain text and replace that with the encrypted MIME part. Okay, that email is now sent it's now captured by Eve and sent to Bob. What Eve now does is she builds a new email with a different structure where she wraps the encrypted part into two further MIME parts which contain HTML. So more precisely, for example, she opens, let's say, an image tag or some other back channel in the first part and closes it in the third part. Okay, Eve now resends that message, that specially structured message to Bob. And what Bob's email client is doing, it will simply decrypt the middle part and replace it with the plain text before presenting it to the user, right? And now what happens is that the email client concatenates all three parts into one single HTML document. Okay, you see what's happening, right? Okay, so now the email client's HTML renderer interprets this HTML document as a whole and well, basically will leak the plain text to Eve's web server, for example. Okay, and interestingly, this attack also works for new lines and spaces and other special characters because HTML will just URL encode them before sending the GET request, right? So it's game over, right? I mean, Eve just got the plain text, and she may not only have captured and exfiltrated one single email. So, for example, she may have captured hundreds of emails within years, placed them all into the middle parts of one specially structured email, sent that email either to Alice or to Bob, and therefore make them exfiltrate hundreds of emails, the plain text of hundreds of emails at once, right? There are a lot of variants of this attack, and unfortunately, some of them haven't been completely fixed until today, which I think says a lot about the state of email security, at least when combined with active content such as HTML. Okay, so now Chris will show us some demo for this one.
Yeah, I will show a demo for this direct exfiltration. I will make this a bit bigger, so hopefully you can see this. This is a macOS from the day we go to full disclosure. So we did responsible disclosure for a long time, and then on Sunday we go online with this stuff, and it was not fixed in these email clients, and so we have here an macOS from exactly this day disclosing this. So we have here an email to Bob from Alice. It's confidential. It's written in the subject. You see this. This is a confidential email, and the meeting will be in my office at 11 o'clock. Okay, so Alice now sends this mail to Bob, and Bob gets a new mail. Okay, Bob can read this email. It's encrypted and signed, and can get this. So Eve now obtained this encrypted email. So I will just put it out here, and I can show you that this mail is still PGP encrypted. So if you put it out of the email client, it will be encrypted. So we have an encrypted mail here, and what's now be done is that we have an Python script here that does nothing more than just attaching this image tag in front and putting the closing tag in the end, and then resends this mail as a completely new email to Bob. I can do this, and then it's starting a listener for the attacker server. As you can see is that Bob has a new email now, and this email has a new subject, a new text. We can see here that there's your request, thank you for your request, and so on. And if Bob now somehow views this mail, we can see here, for the first, that we have a completely new text and we don't see the old email the attacker wants to exfiltrate. And if we then look into the attacker server, we can see here a GET request with Apple plain text body, and here the clear text is starting, Dear Bob, this is a confidential email, right, the URL encrypted, the meeting will be at 11 o'clock.
Okay, so that simple attack. So let me come to a conclusion. So the Efail attacks, they actually attack the crypto standards, but also how to interact with non-crypto standards. And well, for S-MIME, this is really bad, right? I mean, as we've seen, S-MIME has no integrity protection at all. So currently, the S-MIME standard can be considered as broken, right? But for PGP, it's different, because PGP has this integrity protection feature. The standard was just not clear on how to enforce it, and it was too easy to do it wrong, right? Okay, so here's some mitigations. Even so, the Efail main contribution, the malleability gadgets, they do not rely on HTML. They're much easier to perform with HTML enabled. So disabling HTML is a good idea anyway, right? Okay, and in the midterm, I hope all of you guys patched your clients. So for PGP, things should be mostly fine now. For S-MIME, it's a bit harder because there are no real fixes. There are no Efail fixes for S-MIME. It's only workarounds like as the email client does not trigger remote content anymore in case that email was S-MIME encrypted and close reported back channels and things like that. So in the long term, we actually need a new S-MIME standard, which is currently being worked on. And we also need to update the OpenPGP standard to do hard failures on missing or wrong NDCs, to disallow downgrade attacks and things like that, which is also currently being worked on. Okay, so last slide, Placket Soundbites. So we think that the crypto standards need to evolve. So just like as in TLS, we need to constantly ask ourselves, is that crypto standard still state of the art? Does it still meet our high demands for security and privacy, right? And also we saw that, of course, crypto without authenticated encryption is basically useless, right? And I mean, all of you guys always knew that HTML email sucks. And it's really hard, given the power of an HTML engine, to write an email client that does not suck when it comes to privacy. But it's even worse for security. But again, it's important to state, Efail is not some HTML issue, okay? Using malleability gadgets, you could also, for example, create a malicious PDF document that, when opened, exfiltrates the plain text. It basically works for all file types that can potentially phone home. But it's easiest to do with HTML. Okay, and Efail, I think, was also some kind of engineering lesson. So if you've got a crypto system that contains of multiple components, all of them may be fine for themselves, but if you combine those components, things may easily break and bad things may happen, right? Okay, so let me come to an end of the talk. So we don't only have a logo, we also have a website and a paper published with all the technical stuff. And come to us to the web room later to discuss, and I guess now we are open to questions. Thank you.
So is it correct that each and every attack that you have just shown can be proved after the fact, after it has been taken place? And do you have any indication that this has been used in the past?
We have working proof of concepts for all these things. We did not see yet that it was used in the past, but we are actually working on some tooling for you to get, for example, an IMAP server scanner, which runs over your IMAP data and can see if the attack was used or not with a really high probability without decrypting your emails. So like looking for some heuristics. This is in work, and we will publish this soon, hopefully. Yeah, would you go? Yeah, perfect.
I was wondering if you can provide what are 2 key points that we should take away from the discussion on the CBC/CFC for chosen plain text? It was I know it was a technical, few technical slides. So what are some 2 key points that we should at least take away from that?
If you use CBC and CFB mode, you should take care that you have some modification detection in place and some message authentication in place to get against those malleability attacks, I think. So I think this is the main key part you should take away here. Yes.
When you're attacking the OpenPGP, is there a difference in how the keys are generated, whether they're in software and hardware, or is it pretty much doesn't matter?
It doesn't matter because the keys, the AES key doesn't matter for the attack because we are just attacking the malleability, and therefore the key itself doesn't matter because you do the decryption or the encryption and then you do the XOR, and there the malleability happens. So for the symmetric key it doesn't matter, and for the public key it doesn't matter either because we are not attacking this asymmetric crypto but the symmetric crypto.
Right. Thank you.